Hey, guess who's back after a long time? So welcome back to Max Made Easy with AB where Max is fun. So we were explaining the concepts of relation and functions and under which we already saw cross product and relations. So today we'll touch upon functions. But we shall recall what we have seen in the last two videos. So cross product is nothing but it's a binary operation between two set. So in the examples we took a to be 1 2 3 and b to be 4 5 6, and so we constructed the cross product, and from that we saw a relation R which is a subset of cross product where A and B, the ordered pair A and B, were related to each other by B equals A plus 3. So that's the link which actually connects the cross product to the relation. Right. So let's consider a particular relation where all the elements in the domain have only one image in the codomain. If you actually didn't understand what do you mean by domain, codomain and image, I think you have to see the previous video that is regarding the relation, and make sure you know those definitions, right? So let's assume that each and every element in the domain have only one image in the codomain, thereby making that relation called as a special relation called as a function. So among several relations that exist between two non-empty set, some special relations are important for further exploration. So that type of relations are called as a function. Do we have other name for functions? Yeah, we have. A function is also called as a mapping or a transformation, right? So the relation f from set x to set y will be a function when all the elements in the domain have only one image in the codomain, right? So the set x is called as the domain and the set y is called as the codomain. To be very precise, the set where we start the mapping is called as the domain and the set where we end the mapping is called as the codomain. And if f of a equals b, that is if we substitute a value a in the function and we get a result b, then b is called as the image of a under the function f and a is called as the pre-image of b under the function f, and the set of all the images of x under f is called as the range of f. So hopefully I made these definitions very clear. Let me get deeper into the concept of functions. Let's consider an example of a relation which is actually a function. So let's define a function f from natural number to integers where f of x equals 40 times x. So since the domain is taken as natural numbers starts from 1, 2, 3, 4, 5 and it goes on, and so substituting all the natural numbers in the function f, we have 40 times 1 equals 40, 40 times 2 equals 80, 40 times 5 equals 200, 40 times 10 equals 400, and it goes on. So the domain is nothing but where we start the mapping from, that's natural numbers. So natural numbers is the domain here, and the codomain is nothing but where we end the mapping at integers. So integers are the codomain here. And let's talk about the range. All the positive multiples of 40 are mapped from natural numbers so that the range is thereby the positive multiples of 40. Yeah. Let's discuss whether all the functions are valid for all the points in the domain. Let's consider a simple example. Let us consider the relation f from real numbers to real numbers. Thereby we define the relation f to be x square minus 4 over x minus 2. So let me substitute x equals 1 here. So 1 square minus 4 divided by 1 minus 2 actually gives you 3 by 2, which is nothing but 1.5, and then let me get closer to 2, and 1.99999 gives you 3.99999, and let's talk about 2 later. 2.00001 gives you the value 4.00001, and if we take the value 3 x values to be 3 and we get f of x to be 5. So, at the particular point 2 we have an undefined value. Let me show you how. So, at the point f of 2, which is nothing but 2 square minus 4 divided by 2 minus 2, which is nothing but 4 minus 4, and that is 4 minus 4 is 0, and divided by 0, which is actually 0 by 0. Yeah, it's undefined. So, this relation can't be a function because at the value 2 we don't know where to map. At the domain R we have 2 and here is the codomain R. We don't know where to map this undefined value. So, this relation is not going to be a function. But I see the graph of this relation passes by 4. How is it possible? Or let me actually simplify this given relation. So, x square minus 4 is actually x plus 2 into x minus 2, thereby cancelling x minus 2, I have x plus 2. So, now I substitute x to be 2, which actually gives me 2 plus 2, that is 4. So, that is why the value, the graph passes through, the line actually passes through y equals 4, but the function does not exist there. But on simplification we have f of x to be x plus 2. So, that is a matter what should be taken. Since the relation does not exist at 2, I exclude 2 from the domain so that I get the relation to be a function, right. So, this particular value where we remove is called as excluded value, right. So, if you want to make a relation to be a function, if some of the values are undefined, some of the values of the function to be undefined, so we remove that value so that I can get the given relation as a function, right. And let us move on to the graphical test of a function. A given relation can be verified whether it is a function or not by a vertical line test, right. So, what do you mean by that? Let us see. A given relation can be said as a function when a vertical line passes through only one point throughout the curve, or else it cannot be said as a function, right. So, let us clear this vertical line test with an example. So, let us consider the graph which we actually saw in relations y square equals 16 times x, which is actually y equals plus or minus 4 times square root of x. I draw a vertical line here and again I draw a vertical line here. Oh, it passes through more than one point, so that this relation y square equals 16x cannot be a function. But hey, let us consider the y axis. It actually passes through only one point, no, 0, 0. Then why can't I say this graph to be a function? Well, the definition of vertical line test says that the vertical line drawn in the curve should pass only one point throughout the curve. So, here I have a vertical line passing through more than one point in the curve, so that this relation cannot be a function even though I have one line which actually passes through one point alone, right. So, this relation cannot be a function. And let us take another example, f of x to be x plus 2. Yeah, this vertical line drawn actually passes through just only one point, and even I can draw many lines, many vertical lines here, and all these vertical lines actually pass through only one point. So, yeah, the given f of x is a function. And okay, let us see a theorem now. A and B are finite set such that n of A to be P and n of B is taken as Q, right. So, n of A is nothing but the cardinality of that finite set is P and the cardinality of B to be Q. Then the total number of functions that exist between A and B is Q power P. Let us see how. So, the given set A have P elements and the given set B have Q elements. Each element in A has Q choices to be mapped to. We can't generalize every functions to be F, we can map as we like, but the definition of function should not be violated, right. So, each element in A have q choices to be mapped to, right? So each choice gives you a unique function and each element has q choices. The total number of functions from A to B is nothing but q times q. So for example, let us take here 1 actually have 5 choices here, again 2 have 5 choices here, 3 have 5 choices here, 4 have 5 choices here, and 5 have 5 choices there, right? So we multiply 5 for 5 times so that I could get 5 power 5. Likewise, I can multiply q p times so that I could get q power p, right? I think I made this proof to be clear. And this is not so important to be learned, but this is a fact. And is it that we could represent function in different ways? Yes, we could. Let's consider a function f from whole numbers to natural numbers, and let's define that function to be x plus 2, right? So we could represent a function using the following methods: the set of ordered pairs, the arrow diagram, and using a table and using a graph, right? So the set of ordered pairs consists of all the ordered pairs where each ordered pair contains the element x belongs to domain and the element y belongs to the range of f, or the element y is actually the processed information from the domain as such. Like if x equals 0, then f of 0 would be 0 plus 2, that is 2, right? F of 0 equals 0 plus 2 equals 2. So we have the processed information here, so that's going to be the second element in the ordered pair. And likewise, f of 1 equals 1 plus 2 equals 3, so the processed information is again right here, and so on. Even I can take whole numbers, I can take 100,000, 10,000 or whatever, right? And how about arrow diagrams? We know that in relation itself, right? We take the domain to be whole numbers as per definition, and we take the natural numbers here, so that I have 0 to be mapped to 2, 1 to be mapped to 3, 2 to be mapped to 4, 3 to be 5, and so on, la la la. And we actually saw the graph in vertical line test, right? So for your information, I just have a small snapshot of the graph, but you know, you could seek the video to the previous ones, right? So let's recall what we have learned today. So among several relations exist between two non-empty set, certain special relations called as functions can be discussed, where each element in the domain is mapped to only one element in the codomain. So this is the definition for a function. And we saw the definitions of image and pre-image, and we saw about the excluded value for certain relations so that that relation could be a function. And we saw the vertical line test of the function, which is actually defined as a vertical line drawn in the curve must pass through only one point throughout the curve, right? And the total number of functions that exist between two non-empty set A and B is nothing but n of b to the power n of a, and a function can be represented using 4 ways, like ordered pair, arrow diagram, a tabular form, and a graph. So good luck, see you in the next video. Tada, bye bye, take care.